All right, so today we're going to be looking at two different equations. We're going to be looking at Charles's law. There we go. Charles was really working with, he was looking at volume and temperature. So he was working with containers that could change just how big they were. Last time we talked about Boyle, he was working with pressure and volume. So he was working with a constant temp. Charles is working with a constant pressure. So if pressure stays the same, he was looking at the relationship between volume and temp. And what he found is that volume and temp are directly proportional. And we have some real life examples that, really illustrate this. When you heat up a bag of popcorn, it expands because the air inside of it gets bigger. Corn kernels pop because the water in them turn into steam, which expand. And so the hotter it gets, the bigger, or it increases in volume. Lussac, so over here, he worked with containers that could not change their volume. So I imagine he was using pretty big steel containers with thick walls. What he worked with was, he was also looking at the relationship between pressure and temperature. And what both of these researchers found is that volume and pressure, when you control for the other, increase by a set amount according to how much the temperature rises. So, one of the things that they did find, though, is for the temperature, we have to be measuring the temperatures in Kelvin, or we have to convert it to Kelvin. To go from Celsius to Kelvin is pretty easy. You just have to take your degrees Celsius and add 273 to it. So the things I would say should be on your shortcuts should be Charles's law, Lussac's law, and then also that conversion right there. Okay, those three things should be added to your shortcut along with Boyle's law. All right, so let's actually make use of these three things here. So let's go clear. All right, so let's look at the practice problem I have down in the lower right-hand corner. So there it says, calculate the decrease in temperature when 2 liters of any gas at 20 degrees Celsius is compressed to 1 liter. All right, so the first question we have to ask ourselves is, which equation are we using? If we include Boyle's law, we're looking at 3 different variables: pressure, volume, and temperature. And depending upon which of those we get, determines which equation we're using. So in this case, they say that we have a temperature. So once again, I'm just going to start listing out variables, okay? Starting off with, they say we have a starting temp of 2 liters. I messed up already. That's okay. Edit, clear. So they want to calculate the decrease in temp when 2 liters, so volume 1 is 2 liters, at 20 degrees Celsius, so that's my starting temp, is compressed to 1 liter. All right, so 1 liter is my volume 2. And right away, they told us what we were looking for right away. Calculate the decrease in temp. So we're looking for T2. All right, so right now, we don't have enough information to get started because my temperature is in degrees Celsius. But I do know what law I'm using. I only have one law that uses volume and temp. That would be Charles's law, which states V1 over T1 equals V2 over T2. All right. Let's convert this temperature into Kelvin. So if it's in degrees Celsius, I just need to add 273 to it. And that should give me 293 Kelvin. All right. So I have 3 out of the 4 variables. I have my equation here. So let's just start plugging in numbers. So V1 is 2 liters. That's over T1, which we converted to Kelvin. We found was 293 Kelvin. That equals V2, which is 1 liter, over T2, which is what we're looking for, so I'm going to leave it T2. All right, so now algebra. Our variables in the bottom. What we're looking for is in the denominator. All right, so before I can begin solving it, I have to get my variable out of that denominator. I've got to get it out of the basement before I can figure out what it is. So the first step, if I'm looking for temperature, is going to be to cross multiply. So I'm going to set these two things equal to these two things. So I have T2 times 2 liters equals 1 liter times 293 Kelvin. All right, now with T2 here, I can do my algebra to get it by itself. So right now I have it multiplying by 2 liters. Get it by itself, we just need to do the opposite, which is divide by 2 liters. And what you do to one side, you do to the other. I have liters on top and bottom, so those units cancel, leaving me only which Kelvin, which is what my temperature is looking for anyway. So now my T2 equals 1 times 293 divided by 293 Kelvin. All right, so let me get out my calculator real quick. Trying to hurry. Where's my calculator? There it is. All right, 293 divided by 2. I got 146.5. And that's Kelvin. All right, now to see if the answer makes sense. Looking at our volumes were cut in half. Okay, so that means our temperature should be cut in half as well. And 146 is half of 293. So I know I did that one right. So the decrease in temperature is we decreased it to 146.5 Kelvin. All right, let's look at one more practice. All right, so down there in the corner, determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees to 30 degrees Celsius. All right, so I want to know the pressure, and they give me a pressure of 1 atmosphere. So my P1 is 1 atmosphere. And they say that, then they give me a temperature, okay? And if it's going from 20 degrees Celsius to 30, my T1 is 20 degrees Celsius. And here they told me T2 is 30 degrees Celsius. And they want to know what the ending pressure is. All right, so in this case, the variables they give me are pressure and temperature. If you check your shortcut, we have one variable that uses pressure and temp, and that would be Lussac's law, which states that P1 over T1 equals P2 over T2. So now my question is, are my temperatures in Kelvin? You look at them, no, they're not. They're in degrees Celsius. So let's just add 273 to both. All right, so in this case, I've got 293 up top. It looks like I'm going to have 303. That's Kelvin on both of those for my T2. All right, the temperatures are good to go. I can plug numbers in now. All right, so we're P1, I've got 1 atmosphere. That's over T1, I forgot the one there, which is 293 Kelvin, equals P2, which is what I'm looking for. So I like to leave it P2. If you want to put X in there, that's fine. That's over T2, which we found out was 303 Kelvin. All right, so now with the variable I'm looking for is up on top, so I don't need to cross multiply or anything. I just need to do the algebra. So right now I have P2 divided by 303. To get P2 by itself, I just have to do the opposite, which is times 303 Kelvin. And what I do to one side, I'm going to do to the other. Kelvins cancel. All right, Kelvin's on top, Kelvin's on bottom. Those cancel. All right, so now I have P2 equals 1 atmosphere times 303 divided by 293. All right, so right now the only unit I have left, which is atmospheres, which is what I'm looking for, so I'm looking for pressure. So let me go 303 divided by 293, since I get to ignore that times by 1. I get 1.03 atmospheres. All right. That's only a difference of 10 degrees. Our change in pressure was 0.03. The big thing about these things that change on temperature is that it takes a huge change in temp to cause a huge change in volume or pressure. So just kind of keep that in mind. That's one thing like mechanical engineers will look at when they're looking at like building engines. Chemical engineers will look at that equipment-wise when they're going to make like vats to produce ethanol, stuff like that. If you work at an oil refinery, you're looking at that because the way that you refine oil is you heat it up, turn it into a vapor. So it's like how much pressure and volume are you having to deal with? And so just going to give you a real-world example of where both of these are used. So yeah, the big things, the big takeaways are look to see what variables are given. That determines which equation to use, and then it's just algebra to get it by itself. All right, I hope that helps out. Good luck.